All right, good day, everyone. Now, a lot of the time, when you're conducting statistical analyses, you're almost always working with variables that contain more than one value. In other words, you have multiple observations. So, for example, if your experiment has 10 different participants, you're going to have 10 different values that you measure, one for each participant. For this reason, our objects can actually represent more than one value at a time. So, for instance, if we want x here to be equal to the numbers 1 through 5, then all we need to do is type a little arrow, the assignment operator, followed by a little lowercase c and some parentheses. And then inside the parentheses, we just type the numbers 1 through 5 separated by commas. So just like that. Then when we run that and we run x, you can see quite straightforwardly, it just outputs numbers 1, 2, 3, 4, and 5. Now this little lowercase c that we're using here stands for concatenate. And this is really just a fancy word that means combine or connect. And basically by combining the numbers 1 through 5 in this way, what we've done here is we've created an object that is technically known in kind of our terminology as an atomic vector. But oftentimes people just sort of shorten that to vector. And what we can do is we can keep using this little concatenate function, this little lowercase c here, to combine vectors with other vectors. So as an example, we could create a vector y, and maybe y here is just, maybe y here is just the numbers 6 through 10. So 6, 7, 8, 9, 10, like so. And we could create another vector, maybe z, and z will just be x and y. So run both of those, and then when we look at what's contained within z, you can see we get the numbers 1 through 10 here. Now, just as a side note, we use this little concatenate function to create a basic set of ascending integers. And, doing something like this is quite common in data analyses. So actually R provides its users with an easier way to achieve this than just simply typing out each number like we've done here. So what you can do instead is you can tell R what the starting and the end values are and just separate them by a colon, and it'll just give you all of the ascending integers. So as an example, if we type A, follow that with our little assignment operator, we type 1:10, you run that and you take a look at what's stored in A, you can see you just get the values 1 through 10. You can also do this in reverse. So if you type something like 10:1, you can see you get 10, 9, 8, 7, 6 all the way to 1. So it's just in reverse. And of course, you could do this with negative values if you wanted. So just like that, you can see it goes -10, -9, -8, all the way to +1. Now the concept of a atomic vector is one that'll have some relevance to people with a fondness for linear and matrix algebra, assuming such people exist. And the reason I say this is because an atomic vector really amounts to little more than a one-dimensional matrix. And we can kind of see how R handles vectors for these purposes by simply performing some mathematical operations on them. So for instance, if we add a single number to one of our vectors here, we can see that R straightforwardly adds that number to each element, that is to say, to each position in the vector. So recall we have x here. Actually, let's do this. Let's clear our console. And let's maybe just, yeah, well, I guess we'll keep all this. So we have x here, and x, you can see, is equal to 1 through 5. If we just simply add a number to this, like let's say we type x plus 2, and we run that, what you can see is that R has added a value of 2 to every element of the vector. So 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, and so on. And if you were to do addition, subtraction, or sorry, if you were to do subtraction, division, multiplication, exponents, they would all work in a similar manner. So we can kind of quickly demonstrate that. So if we did something like x minus 2, whoops, let's do that. We do x minus 2, x multiplied by 2, x divided by 2, and we'll do x to the power of 2. And we run all of those. You can see they follow the same kind of pattern of computation. And this is quite useful when you need to do things like transform your data. So as an example, perhaps you might need to convert a vector that's in inches to centimeters. So let's maybe just illustrate how that might work. So let's say you have a vector and its name is inches and it's got some values in it. So we'll just say it's got the values 1 through 10. Whoops. So if we run that, you can see it's just the values 1 through 10. And what we could do is we could create another vector called centimeters here. And we could just simply say inches multiplied by 2.54 to convert these values into centimeters. So we run that, you can see we get the numbers 1 through 10 converted to centimeters there, assuming they were in inches in the first place. Now, a similarly logical process occurs when we perform mathematical operations on 2 or more vectors of the same size. So recall we have x here, and x is simply equal to the numbers 1 through 5. And we also have y here, and y is equal to the numbers 6 through 10. In other words, both of these objects contain 5 values. And if we add these together, what you can see is the first element of x here gets added to the first element of y, producing a 7. The second element of x gets added to the second element of y, producing a 9, and then so on and so forth, right? 3 plus 8 is 11, 4 plus 9 is 13, and 5 plus 10 is 15. Makes sense, right? But what would happen if we had vectors that are not the same length? So in this example here, x and y have the same amount of values in each. But what if one of them only had, say, 4 numbers? What would occur then? Well, we can actually kind of test this. So we'll create an object, we'll call it z. And z here will just be equal to 1, 2, 3, and 4. So z only has 4 values in it. So there you go, 1, 2, 3, and 4. And what we'll do is we'll add z to y and see what happens. So we'll say z plus y. Run that, and you can see it produced an output, but it also produced a nice big warning message. So in terms of the output here, you can see everything kind of proceeded as it did before. 1 plus 6 is 7, 2 plus 7 is 9, 3 plus 8 is 11, 4 plus 9 is 13. But when it got to kind of this point, then you can see it loops back around to 1, and then you get 1 plus 10, which is 11. So this is something R did out of convenience, but as you can tell from the error message, this is not something that it necessarily wants to do. And I would say as a general rule, you should not be performing any kind of arithmetic on vectors of unequal lengths. Now, thus far, all of the vectors we've created have been numeric vectors in that, they've only consisted of numerical values. But atomic vectors are not limited to just numbers. They can also contain character values and logical values. So as an example, we could, of course, create a vector with just numbers. We could also create a vector that contained character strings. So we could type something like, maybe like bread and spam and maybe another slice of bread. Alternatively, we could have logical values. So we could say true, false, true, something like that. And you can run all 3 of these and shouldn't generate any errors. And if we look, we can see what's contained within each of them. So, it's all pretty straightforward there. What is maybe less straightforward is the fact that you can't actually mix and match. So for instance, if you have a character string amongst a set of numeric values, those numeric values are all going to be converted into character strings. So we can kind of demonstrate this. So if we create an object D here, and we say something like 5, and we say maybe spam, and we say, I don't know, 6, 7, and 8. And you run that, and then we take a look at what D outputs here. You can see D has output, all of these values, but critically, all of the numbers are within quotation marks. This indicates that R doesn't recognize these as numbers per se. Rather, it recognizes them as character strings. And we can kind of verify this by just using the type of function that we used in the previous video. So if we insert D into that, you can see it tells us that D is a character vector. Or rather, it's a vector of character values, if you like. Now, another intriguing feature of atomic vectors is that if you have a set of logical values, those logical values, or actually what I should say is, if you have a set of logical values amongst a set of numeric values, those logical values will be transformed such that true will be equal to 1 and false will be equal to 0, making essentially the entire vector numeric. So as an example, if we create an object E here, and we include the number 666, and then we say true, and we say false, and you run that, and then you look at what is stored within E, you'll notice the true has been converted to a 1, and the false has been converted to a 0. In fact, if you have an entire vector of logical values, you can actually treat the trues and the falses as just 1s and 0s respectively. And this is actually a feature of logical vectors that kind of frequently comes in handy. So as an example, let's move up here. As an example, suppose you have x, and x is set to 100. And actually, let's do this there. Yeah, so suppose you have x, and x is set to 100. And suppose you also have g, and g here is a vector that contains true, we'll say true, true, false maybe. How about false again and true, like so. And you run that. So if we just look at g here, you can see it just contains our trues and our falses. But if we add x to g, so we say x plus g, what you will see happen is basically R will treat these as 1s and 0s. So basically you get 100 plus 1, which gives you 101. You get 100 plus 1, which gives you 101. 100 plus 0, which just stays at 100, and so on. So that's a feature that quite often comes in handy. Now, similar to how R comes with pi, kind of stored as a constant. So recall that you can just type pi, and R will naturally output pi. R also has constants for a few other kind of commonly used character vectors. So for instance, if you type letters, all uppercase, and you run that, you will get all of the letters of the alphabet in uppercase lettering. If you type letters all lowercase and you run that, you'll get the same thing, just lowercase letters. If you type month.name, you'll get all 12 months of the year. And if you type month.ab, that'll just give you the abbreviated versions of the month. Now notice in the output here, we have these numbers inside brackets. And what these numbers indicate is essentially the position of an element in the vector. So for example, if we just look at the output for the capital letters here, The letter P right here is located at the 16th position in this vector. So if you count 1, 2, 3, 4, 5, 6, 7, 8, etc., and you go all the way to P, P will be the 16th element of this vector. If we look at maybe the month names here, you'll notice November is in the 11th position. So every new line that is written to the console here will give a position number of the first element on that line, meaning the size of your console screen is actually going to affect which position numbers actually end up getting displayed here. So you might actually see different values to what I have on my screen, but for instance, the letter P should still be in the 16th position. And it's not by accident that these numbers we're looking at are demarcated by square brackets. So square brackets actually have a special purpose in R. They allow us to index specific values. So for instance, if we want to know what the 17th letter of the English alphabet is, all we need to do is type letters, put some square brackets, and inside of those, type 17. And if you do that, it will give you it will give you, or it will output the element that is in the 17th position of this vector. So that's the letter Q. If we want to list out maybe something like the first 5 letters of the alphabet, what we could do is we could type letters, put some square brackets, and you could type, or you could use the concatenate function and you could type something like 1, 2, 3, 4, 5, run that, and it gives you the first 5 letters of the alphabet. Alternatively, the more efficient way of kind of doing that would be to just go 1:5, like so. By contrast, if we want to list out all of the letters except for the first 5, that is to say, if we want to kind of exclude the first 5, what we can do is we can just include a minus sign in front of our concatenate symbol. So if we type something like letters, and you type a little concatenate with your parentheses, and we could just put 1 through 5 in there. You put a little minus sign right in front of that C, and you run that. What you can see is it outputs, the whole vector here, but it has ignored the numbers 1 through 5. And hopefully this is obvious, but the use of vectors inside our indexing brackets means we can basically select any position we want. So as an example, if we wanted to examine the 2nd, 3rd, 5th, 7th, 11th, 13th, 17th, 19th, and 23rd numbers, so those are all prime numbers. If we wanted to look at, all of those prime numbers as positions in our vector, we could just simply, create an object. We'll call it primes, and we could insert the prime numbers here. So that was 2, 3, 5, 7, 11, 13, what else was it? 13, 17, 19, and 23. Right, we could do that, and then we could say letters and insert primes. Run both of those lines, and you can see we get all of the letters that correspond to the positions of the prime numbers there. Now, one last feature that maybe we should touch upon is replacing values. So let's maybe do this. Let's suppose you have just a vector of zeros. So let's say you have A, and A here is just full of zeros. So we'll just put maybe like 5 zeros. So run that, you can see A is just full of zeros. If we wanted to do something like replace the 5th zero in this vector with a different number, we can actually use our indexing feature to do this. So we could say A square brackets 5, and then type our little assignment operator and input the number we want to replace it with. And if you do that and you run A, you can see now the 5th position has been replaced with 666. And of course, if you want to replace multiple values, you can just apply the concatenate function. So for instance, let's replace the first and third elements here. So we'll use our index and our little concatenate function, and we'll say 1, and 3. I guess we've already replaced 5, so there's no point in doing that. And we'll just replace that with maybe the values 13 and 666. Run that, take a look at A, and you can see the first value has been replaced with 13, and the third value has been replaced with 666. But the second and the fourth value, remain unchanged because we've not told R to change those values. So yeah, that's pretty much all I wanted to cover here. Hopefully you'll learn something, and I will talk to you guys in the next video.